afternoon, everyone. On behalf of the College of Forest Resources, I wish to welcome all of you to this 12th Denman Forest Reissue series entitled Water Supply and Stormwater Issues in the Pacific Northwest. We look forward to an exciting and informative program today as we investigate a series of issues dealing with streamflow prediction, climate change and its effects on water supply and water storage, water rights, balancing water usage between domestic, agricultural, and conservation uses, and the role of forest and forest restoration in relation to water issues. The purpose of the Denman Forest Reissue series is to provide information and discussion on timely forestry and natural resource issues. As with all activities associated with an academic setting, our ultimate goal is to inform and educate our students, faculty, and staff, as well as resource professionals, landowners, and the general public. These programs are made possible through the generous support provided by the Denman Endowment for Student Excellence in Forest Resources, and they support the college's vision of being a world-class and internationally recognized source of knowledge relevant to environmental and natural resource issues. The mission of the College of Forest Resources is to study and investigate the sustainability and functionality of complex natural resource and environmental systems in both natural and managed environments using an interdisciplinary approach across multiple spatial and temporal scales to include our urban, suburban, and wildland landscapes. In our college, we focus on programs in sustainable forestry, sustainable urban environments, and sustainable forest enterprises. Sustainability serves as the goal for all of our programs and includes all resources, such as trees, plants, water, wildlife, or insects, for example, considers the needs of future generations as well as those of the present, and strives for a dynamic equilibrium that balances ecological functions and conditions with social and economic factors. Today, our topic is devoted to the investigation of a series of water-related issues of high importance to those of us who live in the Pacific Northwest. Current and future water supply issues are and will become even more important as time goes by. In the Pacific Northwest, water supply is largely controlled by two factors, geography and seasonal weather patterns, wherein about 2/3 of our precipitation occurs between October and March. These two factors, geography and weather patterns, combine to produce high variation in precipitation across the region, for example, from the western slopes of the Olympic to the eastern slopes, and between major river basins. Some of our rivers are highly influenced by snow events, some by a combination of snow and rain events, and some of the lower elevation river systems are highly influenced by rain events. That's what's depicted on this graph. The red line depicts a snow-dominated river system showing normalized stream flows over the months October through the hydrologic year to September, with peaks in June and July, whereas a rain-dominated, the blue line peaks much earlier in the year in November, December, and then stream flows drop off. So there's high variation just due to the type of river system that we're talking about. Most of our power, irrigation, and domestic water supply originates in the forested watersheds of the Pacific Northwest. So maintaining our forest as healthy, working forest is essential to a sustainable water supply. The UW Climate Impacts Group has been looking at possible changes in the Pacific Northwest climate as a consequence of global climate change. And this slide just hits the very top summary items. Some of the things that we expect to occur over the next century include warmer temperatures, wetter winters, and reductions in snowpack as a consequence of those warmer temperatures. And because of all that, and thinking back to the previous graph, earlier peaks, spring runoffs. The Climate Impacts Group also has looked at possible implications of climate change on our Pacific Northwest water resources. A couple of conclusions are that many rivers will see changes in peak flows between winter and summer. Salmon will suffer if summer flows decrease and water temperatures rise. And low-lying coastal areas may, in fact, be flooded as rivers and oceans rise. And lastly, we expect increased conflicts over water rights and water usage to occur, and increased urban demand for water relative to agricultural demands. Today, we have a group with us to address these and other complex issues. Our speakers are drawn from city, county, state government, and higher education. Our topic, once again, is water supply and stormwater issues in the Pacific Northwest. And our moderator is Bob Edmonds, Associate Dean, UW College of Forest Resources.
Okay. Our first speaker this afternoon is Ann Steinemann, who is a professor of civil and environmental engineering, professor of public affairs, adjunct professor of forest resources, and director of the Water Center at the University of Washington. She received her PhD in civil and environmental engineering from Stanford University and specializes in water and natural resources management. She has interdisciplinary expertise in environmental planning, economics, policy, and public health, and has published several books and advises government agencies and industries on water and environmental issues. Her current studies address climate impacts on water and energy resources, drought management, health effects of pollutants, and sustainability. The title of her presentation is Water Resources in the Pacific Northwest. Ann.
Good afternoon, and thank you all for being here. I'm really thrilled and honored to be able to talk about water resources. And it's linked with forest resources. And when you fly over the Pacific Northwest, what do you see? You see a lot of magnificent water resources, the lakes, the rivers, Puget Sound. You also see the magnificent forest resources, and that's one of my main points, is that the forests depend on the water depends on the forests. And forests are valuable for water quality and water quantity. Now, because of the attractiveness of this area with the water in the forest, these two jewels, so a lot of people want to live here. It's the lifeblood of our economy. And so consequently, we have challenges for resources management. How do we preserve and sustain and manage our natural resources to support the diverse needs? And what I'm going to do with my talk is look at these interrelationships between forests and water and the value that they provide. They can provide some conclusions, and the main one is about sustainability, is how do we sustain and make decisions now that will maintain the health of our natural resources in the future. Some of the main concerns about water in the Pacific Northwest, and our speakers will address these in more detail. Climate variability and climate change. Climate change refers to long-term trends, increase in temperature. The variability is the year-to-year changes, hot one year, cold the next. In the region, we've seen an increase of 1.5 degrees Fahrenheit warming over the last century. The implications for water is that streamflow peaks are occurring earlier. So this long-term temperature trend is affecting the timing of our stream flows coming earlier. And droughts and water shortages. Droughts are the most costly natural disaster in the United States. It can inflict tens of billions of dollars of damage in a single drought year throughout a state. And even though we think we may be immune to droughts because of all the precipitation, droughts are really when supplies are inadequate to meet demands. And demands can include things like environmental requirements as well. On forest cover, that forests are important not only for water resources, but also for the species that depend on those water resources. Power generation, the hydropower is critical to the Pacific Northwest, and it affects energy prices and supplies in the entire western U.S. In urbanization, that the Puget Sound region has seen a growth over the last 50 years of over 173% increase in population. Now, with all that demand comes increased demands and stresses on water supplies. And so we're going to look at urbanization and also effects on stormwater and stormwater management. Endangered species, salmon issues affect water, and sustainability. We'll also be looking at what does it mean to have a more sustainable management of natural resources. Okay, first, some hydrologic features. That we get most of our precipitation in the winter, but most of our demands are in the summer. Snowpack acts as a major natural reservoir. It contributes more than 60% of the water to stream flows. ENSO and PDO, that stands for the El Nino Southern Oscillation and the Pacific Decadal Oscillation. These are both climate phenomenon. They affect precipitation and temperature in the sense that more precipitation will mean more volume, and higher temperatures mean earlier stream flows. The importance of forested lands, I think this graphic illustrates it fairly well. This looks at tree cover density in the Pacific Northwest and also runoff. And the main point of these graphs is that where there's trees, there's water, and there's runoff generation. And the densest areas of trees are where most of the runoff occurs. This shows how peak stream flows are occurring earlier in the Pacific Northwest, in some places as many as 20 days earlier. Now, this has significant implications for management decisions for salmon and hydropower, urban needs, and agricultural needs, because even if you get the same volume of water, if you're going to get it at a different time, that can create management difficulties. Now, some of the features of the water system infrastructure. A characteristic of our reservoirs here is that they're seasonal, that they hold less than mean annual flow. For instance, along the Cascades and the Columbia, they hold less than 30% of mean annual flow. And along Cedar River watershed and those reservoir systems hold about 10 to 15% of mean annual flow. In contrast, the Colorado River system holds several years of mean annual flow. The hydropower system generates most of our electric power, and this is also the swing resource for the entire western U.S. So all the western U.S. is looking at what's happening in terms of hydro in the Pacific Northwest. Recreation depends on the snow and snowpack in several ways. One is, of course, during the winter for the ski industry. Another is during the summer for boating, kayaking, fishing. So recreation is highly dependent on the snowpack as well. And most reservoir sites are already taken. Additionally, we seem to be entering an era of dam removal, and so new storage options are really limited. So the point here is that we have increasing, often competing demands for limited supplies. Give kind of a schematic of the state of Washington is that urban and municipal industrial needs dominate on the west side and agricultural needs dominate on the east side. Hydropower is prominent along the Columbia, and we also have salmon issues along the rivers. Also, the Columbia and Snake Rivers, it's the second largest transportation network in the country, so those are also important for those factors. In terms of precipitation, the west is very rainy, and the east can be arid. So we have almost 200 inches of precipitation around the Olympic Peninsula, going down to about 10 inches on the arid region of eastern Washington. And on both the west and the east side, demands are increasing. On the west side for urban populations, for the east, agricultural. Also, in terms of the way the reservoirs are operated, on the east side, the hydropower is a major emphasis, whereas on the west side, municipal industrial water supply is important. Now, I mentioned that forest resources are important both for water quality and for water quantity. The forested watersheds provide many benefits. And here's a list of just some of them. First is pollutant assimilation, that forests assimilate both air pollutants and water pollutants in on the land. They also moderate temperatures. The tree canopy provides shades for the streams and the rivers, which also helps salmon habitat. It filters nutrients and sediments, provides habitat not only for the species that live in the water, but also in the trees themselves. There's some studies that estimate between 50 to 90% of all species on the planet live and depend upon forest resources. Also, it helps with flood and erosion protection, that it reduces the velocity of overland flow and stabilizes banks. It intercepts moisture and brings that moisture from fog back into the groundwater system. And water supply provision, the forests are like a giant sponge, and they release water gradually. Some examples of the values of forest resources. Looking at their benefits for water quality and avoided water treatment costs, these are from studies conducted in Washington and Oregon about the value of protecting watersheds and forested watersheds and how they can provide benefits in terms of not having to build wastewater treatment plants. And there was actually a case in New York State where the state paid about $1 billion to preserve forested watersheds in the Catskills Reservoir area. And that saved them $6 to $8 billion in avoided costs of building a wastewater treatment plant, and also avoided costs of $300 million a year. So there are clear benefits in these cases of preserving forested watersheds in turn for avoided treatment costs. And the point about the Cedar River watershed sequestering carbon dioxide, there's also another benefit that's been looked at more carefully, is the benefit of forested watersheds as being a way to provide mitigation offsets for carbon, which may become important as we start looking at carbon markets and trying to mitigate impacts of climate change. Now looking at urban examples, a study conducted in the College of Forest Resources found that the benefits of a single tree in Seattle could range up to $53 per tree. And that's both in terms of reducing stormwater runoff, erosion, providing benefits in terms of shade and tree canopy, as well as pollutant assimilation. Also, the tree canopy assists in removing both air pollutants and water pollutants, as well as mitigating the effects of stormwater runoff. And trees also have direct benefits in terms of air quality, that they can assimilate the emissions of driving a car. A single leaf can assimilate 5 times its weight in particulate matter. Now, some of the challenges of valuing these resources. So it seems clear that these natural resources are valuable, but how can we put a dollar figure on them? Well, that was one of the perennial challenges. The environment provides services for free. They provide a source of inputs and also a sink for the waste to assimilate the pollutants. But how can we put a number on this? In fact, there's a study conducted that showed that the value of natural resources exceeds the GDP of all the countries in the world combined. So they clearly have a value, but they may be difficult to quantify. Also, future cost benefits are often discounted. Now, when I say discounted, I can mean that in 2 ways. One is that if we say use a discount rate of 7%, that something 100 years in the future is worth only 1/1000th of that value today. So future impacts, whether they're beneficial or detrimental, are made less relevant in the present. And the focus on trying to make quarterly profits and growth in the short term may neglect the value of resources in the future. Also discounted in the sense that they tend to be disregarded or neglected because there is this focus on short-term decision-making, often at the expense of long-term resource benefits. Private decisions often omit public costs and benefits. This is the classic externalities problem. That is a landowner who puts pesticides and fertilizers on their landscape, in turn then affects the water quality of the entire, say, Puget Sound, because they don't necessarily have to internalize all the effects of their actions. In the same way, we can ask questions as what kind of incentives do we need to provide private landowners in order for them to manage their holdings more sustainably? Also, standard accounting measures exclude natural capital. As an example, if you look at gross domestic product, if we cut down trees and sell them, the GDP is credited for the sale of the trees, but it's not debited for the loss of natural resources. But from future directions is what kind of research and questions should we be asking to provide the science to inform policy decisions? Promoting sustainability. Sustainability is about the 3 E's, classically: environment, economics, and equity. To be able to show ways that we can make environmentally sound decisions, and it actually helps the bottom line and can be equitable. One of the challenges here is how do we develop sustainability indicators to see what is sustainable and as well defining sustainability. Optimizing funding allocation. Given that we have resources dedicated for restoration and preservation and remediation, how do we most effectively allocate those resources? How do we get the biggest bang for the buck and to know how well our efforts are working? We need to incorporate the uncertainties of climate change, climate variability, resources management into our planning decisions. That we don't know how things may be in the future, so we need to consider this uncertainty and also prepare for adaptive management. To value natural resources, that even though they may not have a direct price tag associated with them, to somehow make sure that we do value them and bring them into decisions and policies. And evaluating effectiveness of efforts. For instance, how do we know how well our best management practices are working? How can we tell if efforts to try to preserve riparian habitat can translate into benefits in riparian species? So looking again at how do we know how well our efforts are working? Some conclusions. The water depends heavily on both snow and forests, and that given the increasing demands and conflicts and limited supplies, I predict the water shortages are going to become more frequent and more severe. The value of these resources, the effects of private actions on public goods, and the uncertainties need to be considered in our decisions. And finally, there's one message of sustainability is going to be important for our future. That is, how do we preserve the health and the integrity of these resources that are the jewels of the Pacific Northwest? Thank you very much.
Our next speaker is Richard Palmer. Richard is Professor of Civil and Environmental Engineering at the University of Washington, where he's taught since 1979. He has a PhD from Johns Hopkins University. His interest involves structured planning approaches to water resources, including impacts of climate change on water resources, drought planning and management, watershed management, the use of decision support and expert systems to civil engineering management problems, and real-time water resources management, particularly applied to drought problems. He's developed the field of shared vision models in water resources planning, which involves stakeholders in the model building process. The title of his presentation is Impact of Climate Change on Precipitation and Water Supply in the Pacific Northwest. Richard.
Thank you. Thank you. It's nice to see such a big crowd out today. I need to acknowledge my co-author in this paper, Matthew Wiley. Matthew's a research engineer in my group at the University of Washington. I also need to acknowledge the other two excellent talks before mine and thank them for setting things up so good for me. So what I'll be talking about is the following things. I'm going to be discussing the climate change and climate change impacts on water. And so I'm going to begin by talking about what's happened over the last 50 years and see if there's any evidence there that things may be changing. I'll talk a little bit about how we make use of climate forecasts in terms of doing water resource planning. Then I'll talk about the results of some forecasts that we've made and looking at how climate change may influence stream flows and water supply. I'll say a few words about fish, and it's just a few words. The group had a chance to look at each other's talks yesterday and the day before, and it was recommended I say a little bit about fish, so I will. And then I'll conclude with some suggestions for next steps. So why forecast climate change? There's a famous quote going around about this right now. Well, the future ain't what it used to be. And that's an extreme concern. In my field, we spend a lot of time using the past as a benchmark for what might happen in the future. And if climate change is real, we may discover that looking to the past may not be an adequate way of preparing for the future. So, what could be happening? Well, it's already been indicated there may be shifts in climate, and they could have some really significant impacts. And so three things that are important, and some of these Anne has already mentioned, is that for the water supplies that we have in Western Washington, the reservoirs are quite small relative to the demands that are placed upon them. Second of all, there is already competition between in-stream and out-of-stream use, and that competition is going to increase. And again, the greatest demands occur when there's the least amount of water available. I wanted to show a quick picture here just to keep us focused. I'm going to be talking just about what we would call west of the Cascade watersheds. And so the watersheds you see here are on the Sultan, if you can follow that, on the Sultan River, on the Tolt River, on the Cedar River, and on the Green River. And for those of you familiar with this, the Sultan River provides as a water supply for the city of Everett. The Tolt and the Cedar provides water for the city of Seattle, and the Green River provides water for the city of Tacoma. All of these streams do provide flows for fish, and some of the storage from those reservoirs that are on those streams are operated for fish. And all are transitional watersheds, and you know what that means now. It's been explained to you that all these streams are affected both by rainfall and by snowmelt. Well, what things have already happened? Some things that have happened since the 1950s. In our region, we've seen warmer weather, more variable precipitation, and the snowpack is down significantly. So if you can walk with me, I'm going to go through a series of graphs to try to make this point. So this is a little heavy on graphs for the next couple of minutes. Okay, this figure has a couple of dimensions to it, and we'll try to walk through. If you look at the lower half of the graph, what you see is a series of either cities, but in fact they're weather stations by elevation. So on the far left you see Kent and Everett, and on the right side of that graph you see Stampede Pass and Paradise. And so those are the higher elevation locations, from left to right, increasing in elevation. And then across the top part of the graph, what you see are seasonal temperature changes for 4 seasons, for winter, spring, summer, and autumn. So in the first case, this is a change that's occurred at the weather station associated with Kent over the last 53 years, and this is the rate of change per decade in degrees centigrade that has occurred. So what you see in looking across this is some variability, but in general what you see is both winter and spring temperatures have increased over that time period, typically by about 1/4 of a degree centigrade per decade, all the way through these sets. Another thing that you see, if you're looking carefully, is that there is in the late autumn, or in the autumn, you see at higher elevations, in fact, things getting slightly cooler, but unfortunately that doesn't help us capture snow during the winter and spring. So first message, the trends in temperature have been going upward, and they've been going upward at most stations in our region, and particularly during those periods where we capture snow. One way to look at this is look at what we call the snow water equivalent, how much water is being captured over time. There's two graphs here, a thin and a thick one. And so the thin graph is the observed snow water equivalent on April 1st over time. And again, this runs just about over the last 40 years in this case, at a location that's not terribly high, but also not terribly low, given our where we typically collect water. And there's actually the actual data and simulated data. But the point to get from this is whether it's actual data or simulated data from our models, that there's been a consistent trend of a little less than 2 inches per decade, a decrease in the amount of water that's available on April 1st. And April 1st is used as a measure of the maximum snowpack in our region. So we're seeing a downward trend in the water that's being stored in our watersheds. And as Dr. Steineman said, this is really important to our water supplies. Another thing that's happening over time is actually a decrease in the runoff, and the example that I'm giving here is specific to the rivers that provide water to the city of Seattle. So this is for the Cedar River and the Tolt River, and you see a general downward trend again over the last 40 years of the amount of water that comes off annually from those systems. And then a final graph I would like to point to. Another thing that happens as it gets warmer, water comes off at a different time of year, and so this graph, these two graphs represent the percent of runoff that occurs in March and in June. So March representing the springtime period and June representing the early summer. And we would like to be able to catch as much of that water as possible. So what we see here is that more and more water is running off in March, the early part of the year, and less is available in June over time. And again, from a water supply standpoint, that's a challenge, because it means the streams are getting, in general, drier in June, and we know how much it rains here in July and August, not so much. So it represents how the streams will face more challenges in the future. Okay, a few words about climate forecast. So I have a like all speakers, a fairly short period of time to speak, and I'm not going to talk about climate change and the evidence for climate change. The last lecture series dealt with that subject. So I'm going to move ahead and talk about how we make use of the climate change models that are available and not the justification for their use. Since the early 1990s, a number of research research members and faculty at the University of Washington have been engaged in climate change studies across the U.S. And typically we approach them in a fairly generic way. The generic way is to use the output of general circulation models to have a forecast of what may happen in the future. And I'm going to talk about a particular study that we've done for the city of Seattle. In that case, we use 7 general circulation models These general circulation models provide information at a very broad scale or a very coarse scale. So the next thing we have to do is what we call downscale that information to the local watersheds. And once we've downscaled that information, which is typically in the form of rainfall, and precipitation and temperature, we run that through a hydrology model to try to capture the changes in hydrology that would occur. And then often we run it through some sort of system simulation model, which might tell us how a particular system is operated. So there is a lot of uncertainty at every stage of this, but I would like to show you some trends that come from these results. And just one more graphic, I guess. This is just an illustration of how this works. This represents the general circulation models, this downscaling process I talked about, putting that into a hydrology model that turns the precipitation and temperature into a runoff, and then running it through a system simulation model, and then coming up with a conclusion. This very cluttered graph I'm going to clean up in just a second, but I want to make the point. When we do these kinds of studies, we typically look at multiple general circulation models. And the point of looking at a number of them is to look for consensus. Do most of the models say the same general information? So in this 22 lines that you see here, one line is actually a representation of recent history simulated, and the other 21 are different climate change models and different times in the future. So there are 3 times represented here, the year 2000, the year 2020, and the year 2040. Let me go through and average these climate change models out and see if we get anything that looks more descriptive. So here's averaging over the decades of 2000, 2020, and 2040. So if you take all those runs of the models, look at them over those 3 time periods, 2000, 2020, and 2040, what emerges is a fairly consistent picture. That in the future, April 1st snow depth as snow water equivalent in this particular basin, the Cedar River, will be decreasing, and it decreases fairly dramatically. If you look at the 50% probability level, it decreases almost by half, in fact, a little more than half, by the year 2040. In fact, in general, our predictions are that for the watersheds that provide water for the city of Seattle, like many of the other regions here, we'll have about half the snowpack on April 1st than we've had in the past by 2040. Okay, another way of looking at this, and I think I just want to make this point, is that there is uncertainty about these answers. There's lots of models that are run. And so we try to look at ways to capture this uncertainty. So this graph is actually very similar to the previous picture. But what I'm trying to say in this picture is that in the year 2000, 2020, and 2040, we will see in general a downward trend in the amount of water we have, and we have some ranges of uncertainty. But in general, the trend is going downward, and there's less over time. I'm going to show this in a slightly different way also. Here's an estimate of how much water will come into the system that serves Seattle in the future, in the year 2000, 2020, 2040. Through the months of June and September. And we know those are the low flow months, but those are also the months that we need water for fish and streams, and the months in which we tend to go out and water our lawns and drive up water demands. And so what this says is that between, on average, again, taking the average value, we're going to lose about 5 million acre feet of water that would flow into our system providing water to us. Well, what does 5 million acre feet, 5,000 acre feet mean? What the figure indicates is that the median value will decrease about 6% per decade, so we'll have less water to work with over time. That 5.2 thousand acre feet by 2040 is about the average, and that's about, over a drawdown period during the summer, about 14 million gallons per day, or about 10% of the water demand we face right now. So we'll see a decrease in our ability to provide water to a growing region. Putting that again in a separate way, I want to show you this. Again, we expect the yield. This graph shows what we might call the gross yield of the system, and what that means is how much water it can provide on a reliable basis over time. And again, we see a downward trend. I'm going to go to the next figure. It's generated from a number of global climate models. What that picture represents is that we anticipate about a 6 million gallon loss per decade over the next 40 years. And there's some uncertainty. Let me flip back just for a second. You see an error band there, but I would like to point out that all the slope is downward, implying that there's very little chance that climate change is going to have a positive impact on our water supply system. The ensemble average is about losing 3.4% per decade. Maybe we'll lose as little as 2.4 at a 75% boundary, but maybe as much as 4.4. So you see no positive numbers in this explanation. There is nothing that indicates that climate change will have a good positive impact for us. I said I wanted to say a couple words about fish. Now I'm jumping to the Snohomish Basin. This is from a different study. I just want to say a couple of things about this. One of the concerns, of course, for fish in the Snohomish and their salmon recovery plans is what would happen to stream flows during the minimum spawning period. And so this is the very late summer, early autumn period that this is a model for. And what you see here is two different climate change models. The first top row is one climate change model. The bottom row is a different climate change model. Anywhere you see that there's large decreases in the flows that may be available for fish during this minimum spawning period, which is an important feature. So basin-wide, we're looking at changes by somewhere between 15% based on one model and 22% based on another model into the future. That will have pretty significant impacts on fish. So what do we do about planning for climate change? Well, I'm going to say a couple of things. One is that Dr. Steinman pointed out we've already seen a change in temperature. I would say by 2040, plan for 2 to 4 degrees Fahrenheit warmer temperatures. That'll depend upon elevation, that'll depend on location, but look for a warmer climate. Look for reduced winter snowpack, and look for reduced summer stream flows. Longer drawdown periods for water supplies, meaning that if we keep the same amount of storage we have now, it'll have to last a longer period. We anticipate some impacts on water demands, but I do need to say that this region has been a real poster child for effective conservation, and we've learned to deal with less water. And so the impacts on water demand are unknown right now, and luckily we've been decreasing water demands due to good changing habits. A point I would hope to make today is that we need to incorporate climate change into our planning. If we move ahead planning the way we have in the past without thinking about climate change, we may have a rude surprise. Always seek regional solutions. The fact that the region has multiple ways to address decreasing water supplies through recycling, through connecting the systems where there's a chance to make use of regions that have more water, those are probably good solutions. So look for these robust solutions that work during droughts. Final conclusions. During the next 50 years, during the past 50 years, we've seen warming, we've seen decreased snowpack, and the hydrologic regime has shifted. Don't expect that to stop, and I would say anticipate it to continue to change. These trends that I showed you for the Cedar River and the Tolt River are not just in those rivers, they're throughout the region. Our studies all suggest warming, lower snowpacks and reduced summer flows. This is going to have impacts both on water supply and our ability to provide water for fish. And again, regional water supply planning should include the impacts of climate change. Thank you very much.
Our next presentation is by Alan Hamlet. Alan is a research scientist in the Department of Civil and Environmental Engineering at the University of Washington. He's been a core member of the University of Washington Climate Impacts Group here on campus since 1996, studying the impacts of climate on Pacific Northwest rivers and water resources systems. He's primarily focused on the Columbia River Basin, including studies of the effects of climate variability and climate change, use of climatic and hydrologic models for long-range stream flow forecasting, and utilization of long-range stream flow forecast and climate change scenarios for water resources planning and management. The title of his presentation is Hydrologic Forecasting. Alan.
Thank you very much. This talk will be an overview of some of the issues associated with hydrologic forecasting, and at the end of the talk I'll give a number of examples of some forecasting systems that I'm familiar with and try to make some points about how these kinds of forecasting systems are designed and what are some of their strengths and weaknesses. To begin with, just some background to help us understand how these hydrologic forecasting systems work. Winter climate in the western United States is probably the primary determinant of hydrologic variability. Now, certainly we have precipitation in the summer months. In some places we have quite a lot of precipitation in the summer months, but most of it evaporates and does not wind up affecting our river flows significantly. So winter climate really is what we need to worry about most in terms of hydrologic forecasting. Now, in the western United States, there are very strong variations spatially associated with proximity to the ocean and also related to topographic variability. And you can see this quite clearly in these two figures. In the left panel, we see midwinter temperatures over the domain averaged over a long period of time. And then in the right panel, is the cumulative precipitation from November to March, which corresponds roughly to the snow accumulation season in the western United States. A couple things I'd like to point out. If you just look along the west coast in the coastal regions, what you see is it is much warmer and much wetter than the rest of the western United States. And this is really due to the proximity to the ocean. Now, the rest of the domain is much drier overall. And if you compare the temperature and the precipitation, you'll notice that the wettest places in the right panel are also the coldest places in the left panel. And what that suggests is that we are seeing higher precipitation in the mountainous areas, which of course accumulates as snow. So snow is a very important part of hydrologic forecasting in the western United States. Now, you've seen this picture before, and I'll just make a few points. Temperature is a very important determinant of when the flow comes in a river in response to precipitation. So what I've done to show this is I've normalized the observed flows from 3 different river basins in the Pacific Northwest and compared the timing of runoff from each of them to the timing of precipitation inputs that ultimately produce those flows. And so shown in the dashed dark line, that's the timing of precipitation averaged over the entire Pacific Northwest. Now, in warm basins that are above freezing pretty much for the entire winter, this is the Skokomish River in the Pacific Northwest, pretty much the timing of streamflow follows the timing of precipitation. If we move into colder areas, like the west slopes of the Cascades, and so this sort of aqua color line that you see there, that represents the Cedar River Basin in the western slopes of the Cascades, you can see that something very different is going on. In the early parts of the fall, when the basin is above freezing, it pretty much looks like the rain-dominant basin, the Skokomish. But as we move into the midwinter, some of the basin is below freezing. The precipitation is being captured as snow. We don't see as much runoff, despite the fact that we have a lot of precipitation. And then in the spring, that snow melts. So we have a dual peak system, a peak in winter and a peak in spring. In very cold basins, like the Columbia River Basin, pretty much all of the precipitation is captured as snow and then melts in the summer months, and we see this large peak. Now, this has some very important implications for climate change, as has been pointed out by the 2 previous speakers. This slide is just to show that urbanized basins have some very important features that are different from natural river basins. This is a slide looking at some hydrographs for Des Moines Creek by Derek Booth and colleagues at the University of Washington. If you look at the broad band of gray on the figure, that's the pre-development conditions. And if you follow that, you can kind of see it down in the bottom there, where it's a fairly smoothly varying hydrograph in time. When we have storms, as in sort of the period centered around March 11th, shown in the figure there, you can see that we're not getting a large amount of peak flow. Now, in a basin that has been developed, where the topsoil has been removed, and we have put down a lot of impervious surface, during those storm conditions, we can see runoff, peak runoff occurring on very short time scales that's 5 times what it is in the natural condition for this particular basin. And base flows in the dry periods are about 50% of what they are in the natural condition. So hydrologic forecasting systems for this kind of basin have to take these kinds of issues into account to do a good job of forecasting. We often think of climate as something that is stationary in time, but in fact that's not really true. And this figure shows the effects of the Pacific Decadal Oscillation and the El Niño Southern Oscillation that Ann Steinemann referred to. Now, what's shown here is for each year the April through September average stream flow in the Columbia River Basin at the Dalles. And I've composited each of these time periods associated with cool and warm PDO. These are shown as the sort of vertical bands, if you will. And the dark line then is the average for each of those time periods. So you can see that the PDO is associated with step changes in the mean amount of precipitation that we have during the wintertime that affects the streamflow in the summer in the Columbia River Basin. Now, the El Niño Southern Oscillation, by comparison, tends to control the interannual variability about this shifting mean. The red dots here on the plot are all of the El Niño years, for example, and you'll notice if you look in each of these bins, the El Niños tend to be in the lower two-thirds pretty robustly across this varying landscape of climate. So together, these provide a way of understanding how precipitation will vary in time. And because we have forecasts of these climate phenomena, we also have forecasts that can be used in terms of understanding what is the variability of future precipitation. And we use these in hydrologic forecasting systems. Lastly, global warming is threatening the amount of water that we have stored as snowpack in our basins. And this is certainly an issue for planning, as Rick has pointed out so nicely, but it also affects our interannual forecasts of streamflow because warmer temperatures are shifting the timing, and if we don't take that into account, we may get the timing wrong. When we're thinking about hydrologic forecasts, one way to characterize them and to understand how they work is to think about the lead time of the forecast, which is just the time between when the forecast is made and when the impacts that you're trying to forecast occur. And for purposes of discussion, I've divided forecasts into three characteristic time frames. The first I'll call short-term forecasts, and these have lead times on the order of, say, an hour to approximately a week. The primary determinant of these kinds of hydrologic variability are weather scale events, so individual storms that come in and deposit precipitation on a basin. These determine what the flows will be over the time scale of a few days. And these are used for flood forecasting, short-term hydropower management, and those kinds of applications. Now, at longer time scales, we also have the ability to make hydrologic forecasts. And these I'll call seasonal to interannual forecasts. And they have lead times on the order of a single month out to perhaps even a few years in some cases. Now, the primary determinant here is not really individual storms, which we can't predict that far in advance. But we try to make use of climate forecasts and other kinds of information to understand the seasonal nature of changes in precipitation and make seasonal volume forecasts, for example, trying to predict summer stream flow in particular basins. And these have wide application for water resources management, ecological management, and other uses. Now, I won't talk about climate change in any great detail, but this is another time scale of variation that we can capture in hydrologic forecasts. And here, really what we're exploiting is the fact that we expect the temperatures to essentially monotonically rise through time over the coming century. So we have information about streamflow timing that is fairly robust, we feel. At these time scales, there's also issues associated with land use, which may become more dominant than they are now. Particularly, how will our forests respond to climate change is an important issue. So how does a hydrologic forecasting system work? We have basically two kinds of inputs that we exploit and try to relate to future hydrologic variability. The first is the initial hydrologic state, which is primarily how much water is stored in the soil column and in snowpack. Then we also have certain kinds of information having to do with future temperature and precipitation variability. And we have essentially a forecast of how much water is likely to come in the form of precipitation and then how much is already stored in the basin. Now, using various kinds of tools such as hydrologic models, which can be very simple, maybe a regression equation or something more sophisticated, we can then relate these inputs to hydrologic variables such as streamflow, soil moisture, snowpack, evaporation, and so forth. Now, these inputs to a hydrologic forecasting system, the relative contribution of each of them is not stationary in time, even in a single year. And to show that, I've constructed a simulated water balance for the entire Pacific Northwest. The sort of aqua-colored line there is the precipitation input. So this is where the water is coming from. And the dark black line is runoff, and the red line is evaporation. Now, on a long-term mean water balance like this, the input equals output. So precipitation, essentially, minus evaporation is what we get as runoff in the river. But there are these large storage terms in basins that accumulate snow. And that's shown in the blue line there. That's the change over the seasonal cycle of snowpack. And also soil moisture is capable of storing a comparable number. So if you think about a forecast that is trying to predict, say, summer stream flow, and we have a forecast date of October 1st, we have very little information about water stored in the soil, and there's essentially no snowpack. So pretty much all of our uncertainty is focused in the precipitation forecast. So that's one time frame. If we're trying to forecast the same thing, summer flows in the river basin, but we are on April 1st, we have a very different condition. We have a lot of information about how much water is already stored in the basin, and the precipitation uncertainty certainly is there, but it plays a much smaller role than it does earlier in the year. So the skill and error characteristics of forecasts are very different at various different times. To finish up, I'm just going to describe a few forecasting systems, how they work, and some of the limitations and strengths of each. The first is a short timescale flood forecasting system that was originally developed at the University of Washington as part of the Puget Sound Regional Synthesis Model, or PRISM effort. This tool has also been commercialized now and is used by the Corps of Engineers and other water managers to manage floods in the region. The system uses a fine-scale hydrologic model called the Distributed Hydrology Soil Vegetation Model, which was developed at the University of Washington. And this model has been implemented over a number of small watersheds in the Puget Sound region. The primary driver of the system is a mesoscale climate model and weather model called the MM5 atmospheric model. And this is driven by large-scale simulations over the globe. With estimated hydrologic conditions, the hydrologic model then can give predictions of stream flow and river stage, which can be used by flood managers. This kind of system is something of the holy grail of hydrologic prediction systems. And the reason that we like these kinds of systems is that they are based on dynamic and physically based tools that have the ability to respond both to unusual conditions and gradually changing conditions without really any adjustments. So imagine that we are now in the year 2050. The oceans are warmer. There may be different circulation patterns. These kinds of tools can capture the effects of those large-scale global changes on these watersheds in the Pacific Northwest without really any changes to the tools themselves. So there's a lot of advantages to this kind of dynamic system. Now, moving to the somewhat longer time frame, the seasonal to interannual time frame, many of the operational forecasting systems until very recently have been based primarily on statistical approaches. And what they do is they measure key hydrologic variables, snowpack being the main one in the river basin, and then using a regression equation for each point of interest, they will provide a forecast for an annual or seasonal stream flow volume. Now, these tools in the middle of the winter work really quite well, but they have some important limitations. First off, they can't provide forecasts that are very useful prior to the point when significant snow accumulation is on the ground, which is about January 1st. Secondly, they have limited ability to look at other kinds of hydrologic variability other than stream flow. So we may be interested in soil moisture or distributed snowpack throughout a basin, or other kinds of hydrologic variables like evaporation. And these kinds of tools don't really work very well in those approaches. One of the major concerns also is that in unusual years, and in particularly in very warm years like what we had last year, there's a lot of questions about how well these forecasts will work because they're based on a fixed training period in the historic record. And the same issues are present when dealing with climate change. Will these forecasting systems remain robust in a climate system that is getting warmer by about 1 degree Fahrenheit every 20 years? That's a question. Now, I think many academic researchers and operational forecasting agencies are aware of these limitations, and so things are gradually moving toward tools that look like this kind of system. This example is from the UW Westwide Seasonal Hydrologic Forecast System, which is being led by Andy Wood in our department. There's a website address down at the bottom if you want to explore this later. But the main difference between this kind of forecasting system and what we see in the operational agencies is that we're using a dynamic, physically based macro-scale hydrologic model rather than a regression equation. They work very much the same way. We need information about the hydrologic state and future temperature and precipitation variability. But again, we don't have the limitations of the regression model and can provide a lot of different kinds of information. This is how the system works. Basically, we spin the hydrologic model up using observed data to produce an initial state for soil moisture and snowpack. Based on observations of snowpack, we can correct any errors that we see in the model based on those observations. And then, using a number of different kinds of forecasts of precipitation and temperature, we can provide a lot of information about what the future might look like. This is just to show that climate forecasts have potentially great value when looking at forecasts on October 1st or so, when we have relatively little information about hydrologic initial conditions. This shows a forecast that we produced last year on October 1st. The range of gray lines that you see there is the range of uncertainty in the forecast. The red line shows what we would assume if we just assumed normal conditions. The blue line is the central tendency in the forecast, and then the black line is what actually happened in water year 2005. So the forecast, before any snow was on the ground, was able to say that there was an increased risk of low flows in this year, which is in fact what happened. Now, these kinds of forecasts have been shown to be better than climatology about 65% of the time based on retrospective tests. And we've shown the value of them in terms of hydropower resources in the Columbia River Basin to be on the order of $150 million a year. So these kinds of forecasts, there's great interest in these kinds of tools. Just a few broad conclusions. We have useful hydrologic forecasts available to us based on weather or climate forecasts, and these range in lead times from a few hours to a few days, even off into the range of a forecast of 50 years or more based on climate change scenarios. Now, many hydrologic operational forecasts are based on statistical methods. However, there is great interest in dynamic systems because we believe they may produce more robust forecasts, both in unusual conditions and in a rapidly evolving climate system. Now, short-term weather models have already produced operational skill in this context, but we face a lot of challenges in the seasonal to interannual time frame that still need to be resolved, but this is where we're headed for. So thank you.